In class example 2.12, we will see how many characteristics of a polynomial function we can determine without using our graphing calculator. Take a minute to try this before you watch through the animations. So first we're asked to determine the start and behavior of the graph. We know that this relates to whether the function is of an even or odd degree and whether the lead coefficient is positive or negative. Because we're of odd degree, we know the arms will point in opposite directions, and because our leading coefficient is positive, we know the right arm will be up. So we can say that we start negative in quadrant 3, meaning down and left, and positive in quadrant 1, meaning up and right. When asked to determine the number of x-intercepts, we'll picture the possible cases. In this case, we could have at most 3 x-intercepts. That's because the degree of the function is 3. That represents the maximum number of times we can cross the x-axis. However, we'll notice that because this is an odd degree function, it's not possible to have 0 x-intercepts. Similarly, because this is an odd degree function, and the arms are pointing in opposite directions, this graph will go from negative infinity to positive infinity in the vertical directions, meaning our range will be all real numbers and we will not have an absolute maximum or minimum to the graph. Note, because it's a cubic function, the graph can have local or relative maxima or minima. If you look at any one of these graphs, let's say the one on the left, you'll notice there is that first peak. That would be called a local maximum because the peak point is higher than its two neighbors, but is not actually the highest point of the graph. All polynomials have a domain of all real numbers. This does not change depending on the degree, nor whether they're odd or even. Our y-intercept, as discussed earlier, is calculated by replacing x with 0. When our equation is written in general form, as it is here, the y-intercept shows up as the constant term. Though it is likely not necessary to use our graphing calculator to find the y-intercept in this case, it will be helpful to find the x-intercepts. Here, after inputting the graph as y1, we'll press second, calc, and then choose option number 2 to determine the zeros or x-intercepts of the graph. By giving left bound and right bound restrictions in the second calc 0 steps, we can find that our first x-intercept is at -2 and 0. Repeating this process, we can find our other two x-intercepts as being +1 and +3. These values could also be found in the table of values by finding which x-coordinates corresponded to a y value of 0. As stated earlier, because this graph is of an odd degree, there will be no maximum or minimum. So the range will be all real numbers. Example B has a lot in common with example A. Obviously they're both polynomial, but importantly this one is still an odd degree, even though it is 5 rather than 3. Its lead coefficient is still positive, and actually happens to be the same value of 1. But what is different here is that in part A we saw a constant term of +6, and here we don't see a constant term, which basically means our constant term is 0. When we have no constant term or a constant term of 0, that means that our y-intercept will be 0, meaning the graph actually passes through the origin. So that means that that point is not only the y-intercept, but is also an x-intercept. Let's walk through this. Because we are a positive odd degree function, we will start negative in quadrant 3 and end positive in quadrant 1. Because our degree is 5, we have a minimum of 1 intercept and we have a maximum of 5 intercepts. Because we are an odd degree function, we do not have an absolute maximum or minimum. Because we are polynomial, our domain is all the real numbers. As stated earlier, our y-intercept is 0 because there is no constant term, which is to say the constant term is 0. And if we subbed 0 in for x, we would evaluate to find that y is equal to 0. Using our graphing calculator and second calc 0, we can determine our x-intercepts. Again, I will note that in this case we could have used second calc 0, or we could have also used our table of values. Now, the reason someone would not want to use the table of values to find x-intercepts would be in a case where they were not integer values. So if you get something like -1/2, that's not going to show up in your table of values unless you've adjusted the table setup a little bit. It's also worth noting here that when we look at this graphically, we see that the x-intercept at -1 is a bounce, which is to say what could have potentially been 2 intercepts was only 1. And that explains why we only find 4 answers instead of the maximum possible of 5 here. Again, because this is an odd degree polynomial, our range must be all real numbers because we extend to -infinity and +infinity. So hopefully those two examples have you feeling really confident with start and end behavior and domain and range, among other things.